computing similar decomposition is too expensive. It's only a constant factor no. It doesn't change the polynomial complexity, but the concept is too large to tolerate in practice. So there's great aversion to using this unless it's in the bit. So on the other hand, you do have P1 and P2, and we barely use those when we use the descriptive data factorization. So one great push was to figure out, is there a better P1 and P2 such that when you look at U, it looks like sigma. Okay, so it was the first one that was done. And there's a table which shows if you take these two, the diagonal of this matrix R is almost equal to sigma. And it's called strong rank driven interval. It's a paper like blue and I understand. And most of the time in practice, when you want to use the SPD, this is the algorithm you should use. There's only one downside to it. There's no good implementation floating around. So if you contact Professor Blue at Berkeley, he still has some MATLAB code that you can go out, but I think his Fortran code doesn't compile anymore. But at some point, I'm hoping that there are the same version of this algorithm floating around. It's about twice as expensive, maybe 3 times as expensive as our use, so it's not like 100 times as expensive, and it does usually a good job. There's also a version of this for the LU factorization, it's called strong RR LU factorization. So RR means rank revealing. This is rank revealing, and it's by you and one of the students. So these algorithms are significantly more complicated because they have to solve some optimization problems in a weak way. So it requires a lot more effort to understand how the algorithms work. So I won't say much about it in this class, but there are definitely the papers that you need to read. Okay? Easy as papers can be. So if you need to feel the SPD and you want the cost, and there's an alternative that I should mention. Alright, so next. So with this, we're basically done with finite system equations. You should know, finite system equation, the same thing as saying you go to the Gaussian. Okay? And Gaussian is non-trivial to do by hand, so much of the difficulty goes with that. So always look for Gaussian elimination. Okay? They can be hidden in various forms, so you should learn to look for it. And once you spot it, the proofs will become much simpler. Now, what we're going to do the rest of the class is infinite dimensional systems. So there, of course, we repeatedly use this LU factorization management. Okay, so you have to get really, really comfortable with Gaussian. It sounds trivial to say it, but as you see by now, it's kind of hard to execute in practice, right? So, for example, when I gave you equations of this form, x equal to z and y transpose a is equal to w like this. Yes, these are all linear operators, right? In this case, you can say this is a linear operator that takes unit A and returns the stuff of z comma w. Right? And it's linear because we take alpha A plus b and return the tuple corresponding to alpha that is linear plus A plus L of w like that. L of we'll do this. So it's a linear operator, so we know just from the abstract mathematics that means you can write it as a giant linear equation. Always you can do this. Okay? So you can always bite the bullet, put all the numbers from x and y somewhere over here, put all the numbers from the unknown a somewhere over here, and put all the numbers from z and w somewhere over here. Right? There's always this representation is possible. Okay, that's the first thing you should do. Check if it's linear. If it's linear, you should, in your mind somehow you should visualize it. Okay, there are many clever techniques for doing this. Right? It's a persistent problem in mathematics. If you talk about PDs now, they look like this. Okay? So you always have to do this association using Kronecker product, but even if you don't know Kronecker product, you can look at a little 2x2 system, write this thing down and see the pattern. Right? So talking about the solvability of this problem, right? Are the constraints on Z and W? Is there a null square? The left null square, right null square? What's the size? How many solutions should I find? But of course, depend upon the size of this function first, and then when you can do any factorization. Right? That's what. Always it will be coupled like this. Right? Of course, sometimes the structure here, if you take a bad ordering of the rows and the columns, the structure here will look very weird and it might make the algebra even harder. Right? So you can spend some time trying to reorder the rows and columns and make it look pretty. So that's you can take a lot of time in real life too. Or you can sometimes work directly with the matrices like this. Okay, but in the end, in real life, most of the time you have to work working you will flip flop it between these items. Okay, so here for example, the unknowns were in a rectangular array, so we take the tensor of rank 2. In real life, you get tensors of rank 3, 4, 5, and so on and so forth. So then, this matrix notation may not be very helpful at all. Okay, if you're forced to write something like this, or people will just write down index notation. A aij x j making aij x j k d I k like that. At some point, the pretty manipulation might just fall apart over time, and you might be forced to think about it. Okay, but the abstract stuff, the notion of left null space, right null space, range, dimension, basis, all of that helps us when you look at an operator that's very complicated. It helps us tell us where we're going, how to get there, gives us some guidelines to reach there or not, and so on. Right? And I want you to first do it in some finite dimensional problems, right? So here's the equal to the finite, so you can try doing it over here. And I'm hoping that many of you try some kind of a guess and check strategy backed up by guessing the constraints and the null spaces. Okay, so the same strategy will be followed with the infinite equations, right? So here the headache, of course, is that we don't know what the actual size of it is. We know it's finite, but we know what it is. It's almost the same headache when you're working with infinite systems of equations. Okay, they're infinite, so it doesn't help us. Okay, so we have to come with some alternative means. So whatever we did in those homework, it's the same thing we're going to feel now to move with infinite dimensional. Okay, so it's good to start with an example because unlike the finite dimensional case where we know that there's a brute force approach to the worst case, due to early factorization of this somehow. In the infinite dimensional case, there's no such thing as Gaussian dimension. Okay, so we have to look at examples, and only for some special examples do we know how to analyze this equation. So the vast majority of the equation, nothing is known. You can remember linear equations in this case. Alright. So let's start with an example. So the example we're going to pick is one that avoids calculus. So we're going to do what I call difference equations. Okay, so most electrical engineers would have seen this in their signals and systems class. We talked about discrete signal processing. Most computer scientists would have seen this when we talked about analysis of algorithms. So because at least analysis of recursive algorithms, you would have seen this somewhere. Okay, so most of you should feel comfortable. I'm going to do a quick look at it. And I posted my undergraduate notes on the class website, so you should download it and look at it. And you should definitely look at it, okay? Because the way I teach it, from a linear algebra perspective, it's not like, oh, let me just give you a recipe for it. Okay, so you should definitely look at it because it tries to say what you learned in an undergraduate club, assuming you don't know linear algebra. Okay, so you should first make sure that you get the right, at least one proper recipe for getting everything. Okay, so let's look at this. So a difference equation involves a solution of an unknown. Okay, and this unknown column is countably infinite, so that's we call the unknown as u in this case. It is indexed by all the integers from -20 to +infinity. Okay, we pretend like that. And electrical engineers will denote this signal by this notation u of n. Okay, so they say u of n, it means the column u. Okay, it's just a bad habit. It's just as bad as if you make a calculus book and you stuck with function x of t, that's okay. Solve this equation b squared y prime minus q y is equal to some, let's say, it's 0 and let's say some x and then let's say y of t somewhere else, right? So this t would be here, but there'll be t here, there'll be no t there. It's just like that, okay? It's this habit of naming the independent variable by a fixed name. Okay, just like operator overloading in C++, but the bad habit of actually fixing the names you will use for variables. It is for a terrible idea, but it's the way mathematics is done, right? We call x-axis, y-axis, yeah. We're used to that, so we fix those names. It's a terrible idea from any perspective, but it's done, okay? So u of n means the column u, not the number sitting at u square bracket n. So even that's also used to mean that. So be a little bit careful when you look at electrical impact. It's very confusing. Are you talking about the number u sitting at 10, or are you talking about the whole column view, okay? And they use the simultaneously. Alright. So in this class, be a little bit careful. If I'm talking about the column u, I'll say u. If I'm talking about the number at u, I'll say u square bracket 0. Or I would say u sub 0. Okay, so this is the mathematical notation with electrical notation, the square parenthesis. So in that case, when you use square parenthesis, it means always the integer will be argument. Okay, just the notation doesn't really matter, right? These are all the same thing. Okay, you should realize by now that a function is long column, so whether it puts parenthesis or subscript should mean the same thing. But of course, if you say something like this in calculus, it means partial of x with respect to t sometimes. Okay, so there's no consistency notation here, so we should pay a lot of attention to this. All right. So what is the difference equation? So the difference equation is, so let's take just a simple example first. We're just going to worry about it. Let's say that we're looking at an equation that holds like this. People usually write the equation like this. Okay, lambda is a constant, probably it's a constant. Okay, so some number that you know, it's a known constant. So you know, say lambda is 2 factors. Okay, and then they people have a habit of writing difference equations like this, including differential equations. So for example, we're talking about differential equations, so this is on the side. Some of you might be more familiar with differential equations. So write them at the same time. So in this case, u is the function of time. So it's usually called u of t. And very few people use the word u of minus 1.3 like that. Okay, so it's all values of u from minus to plus infinity for time. It's all values of real numbers. Use a column index for the real numbers now. Right? So here the corresponding differential equation that is easy to solve, mimics this one will be du by dt is equal to lambda times u of t. That's how we do it. Of course, when you write equations like this, we're so used to seeing them, we think we know them, right? But if we should be a little bit careful. Okay, so what are these equations really telling us? Right, there are a couple of ways to think about it, right? So if we think of it graphically, which it doesn't hurt, we are saying that u is a graph, right? This is time n. This is n-axis, is 0, 1, 2, minus 1, minus 2, like that. Right? So this is 0, minus 1, 0, 0, 1, like that. Here the graph is, of course, t-axis and the sum like that. This is equal to 0. The height of the graph is u of 0. The height of here is t is equal to 1, is u of 1. That. Right? And we're saying that when I say that I don't know these numbers, I'm saying I don't know the height of any of these 6. So really over here, when I say that I use my unknown, I'm saying I don't know the height at any point in time. Right? All of those heights are known. That's what we're saying. We don't know the function. Right? It means we don't know all of those numbers. So the number of unknowns here is clearly infinite, right? There's an infinite number of sticks whose height we don't know. It's countably infinite there. Here, of course, the number of unknowns is the height at every point in time, and the uncountably many such points. The uncountably unknown numbers in that, right? And we only count numbers in linear algebra. So the number of unknowns in both the cases is infinite. Okay, what does the equation itself tell us? So this what it is of course a shorthand for an infinite numbers equation, right? For example, if I look at the discrete case and take n equal to 0, I will get the equation u of 1 is equal to lambda times u of 0, right? Look at n equal to 0 case. Look at n equal to minus 1, I get u of 0. Minus 1 is equal to minus 1, and the equation of that. And look at n equal to 1, I get u of 2 lambda times u of 1, like that, right? So these are the equations, right? There's no n in this. Okay, there's no such thing as n in this equation anywhere. Just like there is no such thing as t in this equation. Right? What does this equation mean, for example? Right? So in the discrete case, in the continuous case, you have, if you look at the derivative of u, that at t equal to 0, it should be equal to lambda times u of 0. What does that mean? So you're saying that when I look at this point, if I look at the slope of this graph, it's unknown because I don't know the height of the graph at any point anyway. So the slope is unknown. So if I look at the slope at this point, it should be lambda times the height at that point. So it's unknown. Right? Same thing, if I look at t is equal to say 0.1, I have du by dt. The slope at t equal to 0.1. So equal to lambda times the height of the graph 0.1. Right? T is equal to minus 1.3, so whatever I have, right? So for each value of time, from infinity plus infinity, there's one such honest to God equation. Okay, you have unknowns that you don't know, multiplied by numbers that you know, and that's a linear equation. Right? So it's just Ax equal to B. But written in a way that you've been trained not to recognize as Ax equal. It's still a linear equation, there's still numbers you don't know, you're still taking all the linear combinations of those. Right? So they're the same equation. Okay, so the same thing over here. For example, what the equation says, if you look at u0, it will be lambda times this one. Look at u of minus 1, it will be lambda times u of minus. Right? It's a linear relationship with the unknown numbers. Right? So it's just a big giant equation, linear equation. If you were to write that Ax equal to, you should the sum. Right? And the procedure for both these equations happens to be the same because the pattern of numbers in both the makers of the error will be nearly the same. Okay, so that is share of procedure for solving it. Right? There's a great similarity in the makers. Okay. So I hope that is clear. Right? So whenever you look at an equation, a differential equation now, the first job is to detect is set to linear, and if it's linear, then you should think of it as a matrix. big giant matrix that you have to solve. Right? And of course, you have all kinds of problems now. Right? So let's just write it out. So let's write in the discrete case first. So we'll write in the discrete case first. So this case over here, we'll go to the question. Then my instinct, of course, is to put all my unknowns together. You should pick a good ordering. So the time-based ordering seems like a reasonable ordering. Right? That might turn to be a bad idea, but anyway, that's the ordering I picked. Then I pick an ordering for the rows, for the equation themselves. Again, I pick the time-based ordering. Might be a bad idea, we don't know. On the right-hand side, I put all the numbers that are known to me. Okay? So let's, for example, at n equal to 0, let's write down. Okay, so I should be careful. Okay, so I need to index the rows of the column because it's an infinite matrix. It's hard to know where the column multiplying with 0 lies. So it's conventional to for example, some people like to put a black dot like that. So which column goes to 0? Some people like to put the black dot in the middle, saying that is the 0, 0 entry. Okay, so you know where the what you're going to call 0 to go, right? You know where it is otherwise. And so there's no starting and stopping of this matrix. And you want to know where the 0th column is, so you know which number is actually going to multiply with 0. And how do you know it's not this one? So you would specify that. Alright. Usually a square block is drawn somewhere on that number. So let's just say this is the one that you're going to take as u0. Right? So if you look at the 0th equation, at time n equal to 0, it is u1 equal to lambda times u0. Right? And like this u1, that is u1 minus lambda 0. So u1 is the number here. So I put a 1 there. So I put a minus lambda here. Right? And similarly, I put n equal to 0 equation on the right hand side. Let's just not make it 0. Okay, so let's add something to it. So let's say that this equation is plus some number x of n, x of n is a known sigma. Okay, so then the equation will read this plus x0 plus x of minus 1 plus x of 2 like that. Okay, and we'll assume that this array x is equal to x. So then this will not be 0, but it's x0 in the first equation. If you look at the time n equal to minus 1, let's write down the equation over there. You depend upon minus lambda of 0 minus 1 and 1 times 0 0, and that's equal to x minus 1. Like that. Right? If you look at n equal to 1, you'll see that minus lambda here and the 1 there, x of 1 there. And now the pattern is obvious, so we can write it down. Okay? So you can see that this time will always be minus lambda, this time will always be 1, lambda 1, and these numbers you can fill out from the array x. That is the equation. Right? So now, remember the first thing you do always is count the number of rows and columns, just so that you know where your difficulty is going to come from. In this case, we see that it's an infinite number of rows, infinite number of columns. Right? So the temptation is to think that this is the square matrix. Right? So the temptation is to think, oh, this matrix will be generically connected. Oh, it's a square matrix, so it should be invertible, it should be a unique solution, and all of that. But of course, by now, all of you know that this system does not have a unique solution at all. Right? In fact, if you even set x to be 0, we get solutions. So it clearly cannot be unique. So if it is squared, it's definitely singular. But it turns out that in the incremental case, things are never that simple. Okay? When you count infinite number of rows, you cannot be sure whether it's going to be like a square matrix, scheme matrix, or pattern. It can go either way. Okay? So infinite-dimensional linear systems behave a little bit differently from square systems. You can't spot square, skinny, fat, full column rank, row rank, that is doing. Okay? So you have to be a little bit more careful about it. So it turns out that to this system of equations, you can add a boundary condition. Okay, so to this system of equations, you can add a boundary condition. So for example, let's take the boundary condition n times u of n is equal to 1. So I add up all the numbers, take u of n multiplied by n, add it all up, and I want that to be 1. Okay, that's my boundary condition. It turns out that after I set this up, then the equation actually is well posed. Okay, there's always really at most one solution. Most of the time, will exactly be exactly one solution. Okay, you still be a little bit careful because there's a chance that for some choice on the right hand side there will be no solution at all. Right? It might be out of the range space of this operator. So if I add the last equation, I can add one more row at the bottom. So I put n equal to 0, I put a 0, then I put 1, 2, 3 like that. Here I put minus 1, minus 2, minus 3 like that. Right? Notice that this thing doesn't come down, but I have to add one more row over here with this 1. That last boundary. Okay, so now if you count, you see that on this side I have infinity plus 1 number of rows. Okay, you can't write this infinity plus 1 as infinity again. Okay, so we are using what's called ordinal arithmetic now. Okay, so the ordering matters. Okay, so this side is using the ordering desk method because that's ordering on the other side of the process. And the number of unknowns, of course, is still convoluted. Okay, so we call convolution theta as omega, then we got the number omega plus 1. That's the side of this matrix. Okay, it doesn't matter. Okay, but you have to pay attention to this matter, this oddball row hanging around at the bottom, which captures the boundary conditions. So for all PDEs and ODEs, this effect will be there. Okay, you'll get something that looks really, really pretty, and then some ugly stuff at the bottom. Okay, it'll be unsymmetric because of that. Right? It's just the nature of partial differential equations and ordinary differential equations that they have this flavor to them. Okay, and of course, this causes enormous headaches in the analysis, but it is going to be there. Okay, if you pay attention to that, it all becomes underposed. Okay, so now the question is, how do we solve this, right? So if we try to do Gaussian elimination, we are in trouble, right? Because there's no first row, no last row. Even if I start eliminating, I will never finish. So people obviously have spent 100 years now looking at this problem. So lots of techniques have been developed, including LE factorizations. Okay, so the people have tried to show that if you do LE factorization starting from the middle and you go two sides like that, eliminate up and down, that you will get a process that will eventually terminate somehow. Okay, you try to get a dynamical system, this infinite thing is an asymptotic value, and you have to compute that. So we take the signals and systems class, you'll see that people in signal processing at least have proceeded like greatly, and it actually can show that under some assumptions, you can actually find the factorization of this matrix, and matrix of similar type. These are called inner outer factorizations and so on and so forth. It's deeply tied to complex analysis. I'll tell you a little bit about how these things are tied to complex. Okay, so here in this class, we won't take that approach because that approach is even more restrictive to what I said. Okay, so we won't go that approach and factorize it. Okay, so we're going to take a much more classical approach so that we first understand what's going on. So the idea is very simple, is that the same idea that you followed hopefully in the other homework problems. The idea is that you first drop some equations that look like oddities. Okay, so they spoil the pattern of numbers you're seeing. So in the PDE case and the differential equation case, generally the tendency is to drop the boundary conditions. Okay, for example, you open a physics book, they never even mention the boundary conditions. Right? So you just drop it. Why? It really, really messes up. Right? These numbers can be arbitrary numbers depending on how I take my boundary condition. And it doesn't follow any pattern that you see on the top. Right? Here it's clearly a Toeplitz matrix. This is the doubly Toeplitz matrix. Right? We play a big role in second processing. So in mathematics too. So this is Toeplitz, but if I put this over here, it's no longer Toeplitz. Okay, so you drop this, you get what looks like a square matrix. So you notice that there are other properties this matrix has too. If you pretend that this is the main diagonal, you pretend that this is the main diagonal, okay, so then that matrix looks like it's an upper triangle matrix. Right? But it's an upper triangle matrix, you've already done Gaussian elimination on it. So in principle, you should invert this matrix. Right? But notice that this is a little bit misleading because what happens if I say, no, I want to think of this as my 0, 0 entry. Right? It's the same matrix, you can think any way you feel like. Then if you think of this as your main diagonal, then this looks like a lower triangle matrix. Well, that's still good because you still don't need to do LE factorization. But now, if you try to write down this inverse, you get a lower matrix. Okay, so if you think in the first way, you look at the upper equations, you think it's an upper triangle matrix, you compute its inverse using the formula that I gave you, or by just guessing, for example, you will find that the inverse is actually an upper matrix, upper triangle matrix. Okay, so these matrices are called upper matrices, or it's called upper inverse. Or for us, it will be called causal inverse. Okay, that's the single processing name for it. If you look at the same matrix and say this is lower triangle instead, then the inverse would be lower triangle. It's called lower because it's really not a square matrix, so people call the word lower. And then that will correspond to what in single processing is called anti-causal inverse. Okay, so the same object can pretend to be upper triangular, lower triangular, and depending on how you look at it, you can either have upper inverse or lower inverse. And if you look at it in this case, you see that if you take one version of it, the entries of inverse will increase, and the other version of it will decrease. So we say in one case that the inverse is stable, in another case that the inverse is unstable. Okay, so all things that you should have heard in the electrical engineering class in terms of impulse responses. Okay, so we'll come back to that a little bit. Okay, so that is one way, right? But if you step back and think about it from a linear algebra, so you can see that ambiguity of treating it as a square matrix, right? You can, it's clearly more than one solution already. So we know something is wrong, we shouldn't even be talking about the inverse. We can't have two inverses. Alright. So So what's going on, right? So let's think about it. Let's say that our ansatz, right? We know because my teacher told me that this giant system equation has a unique solution, right? So then we know that if that is the case, then logically this is the square matrix, right? So we should have number of rows, max number of columns. All right. If that is truly the case, then if I drop a row, then I should get a fat matrix. Even though it doesn't look like that to my eye, if I drop a row from a square matrix, I should get a fat matrix. Conceptually, that's what we should expect. Therefore, if this is a fat matrix, you should have non-trivial null space. Right? So if I compute the null space of this star, then it turns out that you can assemble the rest of the solution. Okay, so this is the strategy that is the most common strategy in differential equations. Okay, so what you do is like this. You say, so let's step back and look at the 30,000 feet view. We have a square system of equations, Ax equals b. Okay, so now I hide the fact that there are some infinite rows of columns. We drop some rows from the equation first. Okay, because it's too hard to guess the whole thing in one shot. Okay, we want to guess, but we want to get fairly simple solutions. So we split the matrix into rows A1 and A2. Because the big matrix A is square, in our head we're thinking A1 is a fat matrix, even if the count tells us otherwise. A1 is a fat matrix. That's what we have. Right, so the top set of equations now give A1x. We split this into B1, B2. B1, B2 is equal to B1. Right? We need to find the solution of this fact. Remember, we drop some equations. Typically, the one that we drop is the boundary conditions. Right? Of course, we cannot drop it. That constrains the solution. So we have to be careful. We need to find the solution of this equation in such a way that you have a few unknowns left to satisfy the ones that we drop. Right? But we know how to do that, right? So we know from Gaussian elimination that when I solve this equation, this x will have a particular solution plus the homogeneous part. Right? So we know that this xp will be such that a1 times xp will actually satisfy this if you want some solution, typically by guessing. But electrical engineers will not guess. Okay, they will use what's called convolution. So we will, okay, so in other words, we will compute one right inverse of this fat matrix and we write down the particular solution. Okay, so I'll write it down over here. So xp will be, we compute one right inverse times p1. Okay, that's how we will get it. Normally, electrical engineers will write in this particular case, you can show that it will be some convolution of some impulse response times p1. We'll come to that. Okay, so that's the first part. Okay, you have to produce one, but you'll see that to compute this part, you cannot do it directly either. Okay, you cannot find this right inverse without doing some other calculation, right? Because that must be harder than what we're trying to solve. Okay, so we'll set it aside. But conceptually, we need this star. We're going to do it by that. It's a slight calculation. But if we just do this, then there's no hope that XP will satisfy the equation that we discarded, right? Because we ignored it completely. Why should that solution satisfy this, right? Because everything is fixed now, it's not going to satisfy it. So we need some freedom to do this. So the way we know what the freedom is, we need to find all solutions of this star. So we need to find all homogeneous solutions of the first set of equations, right? So we can find a full basis for it. So we find matrix n, let's say C1n is equal to 0. And then the right homogeneous solution is n times some free variable z. Right? If I can find all the columns that satisfy the equation a1 x equal to 0, I can assign the linearly independent set, I can assign them in this column, this matrix n, take linear combination of that to find any other homogeneous solution. Then I can write x as the particular solution that I found plus n times z. I can stick it into the equations I discarded, so I stick it into a2 like that. Equal to b2, right? I know xp times a2 and I can just solve the smaller system of equations now. Right? So the number of unknowns here will be much, much smaller. So for example, here there will only be one unknown. So this equation will be a 1-by-1 equation to solve here. Okay, so that's roughly the procedure we're going to follow. And this is roughly the procedure you follow whether you're trying to put Markov equations, Navier equations, a simple difference equation or not. Okay? So this is roughly the procedure. So you discard some equations. You take the fat part. For the fat part, you need to find all solutions. So you do that by first finding the null space solution. Okay? Once you find the null space solution, then there are techniques from n to construct the right inverse. Alright? That's how we're going to go. Okay, so this method of constructing the right inverse from the null space solution is called method of impulse responses, Green's function. That's what I know to do with fundamentals. Okay, yeah, so that's the big picture we're going to take. Okay, so remember, we don't have access to LU factorization. So we're trying to reduce the problem that we can guess the solution. So the one that we need to guess the solution for is this guy. I didn't tell you yet how to find the solution. Okay, so this one is the one that is the most expensive to study because this is the path that we know works reasonably well. Okay, so everybody, so these are in the physics, these are usually called special functions that depend upon this operator that's sitting in front of them. Okay, so for us, for example, what is the equation? So let's do it. So for us, the homogeneous equation in our case will be for us it will be, we want to find, right, it will just be the top part of this equation, right, times some column 2 equal to all zeros. So there's nothing to do with the u that you're calling it. We usually put a different suffix, we solve this equation. And on the right hand side is 0, we don't have it. This is the homogeneous solution for us. That's the one that we want to solve. What is the homogeneous solution to the differential equation, guys? It's the same thing. You will have another function you want to compute, to lambda times UH. Okay, there's no x of t outside for that. Otherwise, there would be an x of t just drop that. We're solving Poisson's equation, so let's look at Poisson's equation. So Poisson's equation says there's some domain, right, of two variables, x and y. Go back to the notation, x and y. And there's some graph on top of this domain of u of x comma y that we're trying to solve. Right? And we say, well, okay, I have at every point x and y inside this domain, I have an equation like this. Right? So this is known, u is unknown. But every point x comma y, there's one linear equation we have to solve. The unknowns are the height of the graph u at each point x comma y. Right? So this equation by itself is underposed, and you need to have some boundary conditions, right? So for example, the boundary condition could be that at each point of the boundary gamma, so u of x comma y is equal to g of x comma y on the boundary. Right? So this we call it Dirichlet boundary condition. The approach is exactly the same. It's still a linear equation, right? This is the one that is the yucky part. So you start with this. You start by solving the homogeneous functions, which we then give it as, which is so important in mathematics because this is the leading term in most scalar second order differential equations. So if the right hand side to 0, we call it the Laplace equation. Right? We find the solution of this. These solutions are so important, we put the name, they call harmonic functions. Right? If you are doing electromagnetics, then you might have something like plus omega squared u of x comma y is equal to 0 then, but then it's called Helmholtz equation. Right? So for every partial differential equation that you study in practice, Maxwell, Navier, elasticity, heat equations, you always look at the leading term, parts that matter to you the most. You set the right hand side to 0, you find the solution of these guys. Right? So usually called special functions because they're so important. Then once you have them, then usually there is a reasonable method to assemble the rest of the solution. Okay? And this technique only works. This method, this whole thing that I work, only there's a certain symmetry in the matrix. If I give you a random, suppose for example, I say, here's Maxwell's equation in a media in which I have dielectric, and this method is. Okay, then you have to go to a computer and solve it by computer. You can't do it by hand anymore. Okay, so certain symmetries must hold before this technique is known to work. Okay, so even this technique that I'm talking about holds a very small bunch of equations. In practice, it's far from sufficient. Okay, so for example, notice over here, so if I slide the equation down and shift it to the right, I get back. Okay, I take one row, slide it down, I get the next row, slide it down, I get the next row. Right? So this we call the translation symmetry in this paper. So it's called a displacement structure. Okay, it is this displacement structure that will be exploited to go from this null space solution to the right of this. Okay, the same thing is true in Laplace's equation too. The equation at this point is the same as the equation at the next point. So you have the same set of numbers as long as you move them over to the right spot in the matrix. So again, it's a displacement structure, same thing, 3 dimensions and so on. So as long as these displacement structures are there, we can do this. But suppose, for example, I say, I want this equation, but I look at this equation. Okay, I'm going to say I have sine of x comma y, e squared mu by e x squared plus tan inverse of y over x, e squared mu by dy squared is equal to 0, then you're out of that. Okay, so as soon as you put some material there and you lose this translation symmetry that you need in the domain, the techniques we're talking about that do not work actually. Okay, so you have to be very careful. Even for a very small problem, the technique will be very, very difficult to get at. Right? So it's very frustrating to a student because for every class of problem there is this host of techniques that you can do. But the good news and the bad news is that this way of solving these problems and looking at the symmetry of the matrix has been vastly generalized through Fourier analysis on loops. But unfortunately, that literature is very obscure. Okay? Very, very hard to read what they're talking about. In this class, I won't say much about it. Other than saying that, if you really have to find, if you get a differential equation or an infinite equation that has some symmetries, you cannot directly get at them, the best bet is to go knock on the nearest mathematicians, go and ask them. Okay? It's a very esoteric subject, it's very specialized, it requires deep skills to do these n calculations. However, if you want to solve on the computer, then it's much far easier. Okay, so the computer, you just make the matrix, throw in most rows and columns, solve it and hope for the best. And if you really want to even prove that you do things right, you'll actually convert to the right solution. Okay, so here we're concentrating mostly on the things that we can do by hand. Okay, so we're going to look at this guy now and see why we can solve him. Okay, so I'm going to leave the big picture up, and we're going to look at the homogeneous solution now, and then see why is it that if I know the homogeneous solution, I can write down the rest. Okay, so most lecture is just be a review of convolutions, impulse response, and so on and so forth. But if you have never seen that terminology before, don't be afraid. It's very not a big deal. For what I'm going to say now. So let's look at it. So I have to solve the homogeneous equation in this case, right? So then the homogeneous solution looks like this. It satisfies the same equations, but I drop the boundary condition. Okay, so A subscript, remind me that this is not the solution that I care about, it's just the null space of the right null space. Okay? That's what I'm getting at. Okay, for some problems, the right null space might be harder than the left null space, in which case you switch to the left null space. Okay, sometimes you have to be clever, you must pick partly the right null space, partly the left null space. Okay, so you have to play games, but in this case, we can just do everything with the right null space. Okay, so let's proceed. So, how do I solve this equation? You notice that in this particular case it's quite trivial because you can always compute n plus 1 if you know what u at time n was, right? You just multiply by lambda. So we see then that if I can write a homogeneous solution, it will look like this, right? So if I know the number at the 0th position, right? Let's think of that as a free variable now. Okay, if I pick that to be 1, for example, then the next number should be lambda times the previous number. Right, and this one should be lambda times the previous number, like that. Lambda times the previous number, like that, right? That's what is saying. U at n plus 1 is lambda times the previous number. And if I go backwards, it should be lambda inverse 0, lambda for minus 2, u 0, like that. Right? Normally, this is told you by saying, in your calculus class, we're going to guess the solution of an exponential solution. Doesn't matter. The reason why you guess exponential is because you get this because of this equation. If you discretize it and look at it, you see that's the solution. You will get to the limit, you get e power lambda t equals. Okay, so we go for the differential equation case. The homogeneous solution transfer is du x w t lambda equal h of t. And either by integration or by guessing or whatever, you will say that u h of t constant e power lambda. It's the same thing. So here we are writing u h of n. Can be some constant, this guy u h of 0, or the constant that we're talking about, or a constant times lambda power. So same thing. Okay, so this solution is that identical. Right? In the discrete world, people don't use natural logarithm for whatever reason. They're going to ask me why. We write lambda as lambda. Right? In the continuous world, they always take the logarithm of the lambda below. Right? That's all. Okay, so we write lambda power of n. Remember, this is, if I call this mu, this is just mu to the power 2. So exactly the same. Right, so you should be careful, huh? Because anybody people say some funny things about this math and discrete world analog world. It's just a habit. Okay? It depends on whether you want to take logarithms or not. In calculus, we prefer to write in exponential notation because we differentiate it so much easier, or integrate it so much easier. In the discrete world, we rarely need integration, but we do need summation, in which case we can just use powers in the geometric series. So for most people, they remember the geometry in the lambda power, not each power lambda. Right, so remember this sum, the center of summation lambda power of n, and there is lambda power n plus 1 and 1. Right, so this is the geometric sum, and then for calculus, we have e power lambda t equals to. Right, these are the same formulas, of course. They just look different, and we remember them differently so that it gives us a desire to write things differently, but they're the same equations. Okay? If you look at it, you discretize it, you look at it, looks exactly like this. the same matrix, it has the same null space, and I have a different lambda. Okay. So set it aside. You should fiddle around with this more than I'm talking about. Make sure that you understand why this is the same as that. Right. So anyways, we have the null space solution. Right. And in fact, you can see by brute force that this is the only solution of that. Right. Because of this property. Right. In this particular case, we get very, very lucky. We can guess the null space solution without any factorization at all. Right. This is related to the fact, of course, that you can think of this matrix being upper triangular, lower triangular. And furthermore, you can tell directly by looking at it. Okay. So let me just go back and say what this process was. Right. Why did I say that? So remember, so this is a fact matrix. So there must be a free variable in it. Right. I'm pretending it's already every factor. But rather than taking the free variable at the end or beginning or the end, which does not exist, I pick my free variable to be u0. I take it to u0, take it to the other side. Now that is either upper triangle or lower triangle. So I get into back substitution. If you go ahead and do it, you will get this as a solution. Right? So my guess after that is that did I get all the solutions or not? Very important to get all the solutions, because if you don't get all the solutions, then you will not have enough free variables to solve the boundary conditions that I got. You must get all of them. Right? The number of boundary conditions picked to match the dimension of the null space. That's how you know how many boundary conditions you need. Okay, so if you don't get them all, you will not be able to solve your differential equation again. So you have to find all of the null space solutions. Right? In this particular case, we know, right, because you know that every solution must satisfy this property, and then you can derive this solution. Okay, so all, if you want to go the other way, somebody else gives you some other numbers, take it back and prove that this property must be true. Okay, so we have found all the null space solutions, and only one is a one-dimensional space, right? But it's a constant. So it's a constant times the vector 1 lambda inverse of the max 2 lambda square lambda square. Right? So this is basis for the null space. Right? So therefore the null space of this part A1, we get over there. So the null space of this matrix minus lambda 1 is spanned by the range space of the null space of this is spanned by the sequence lambda part of that. The one-dimensional null space. Alright? So this is usually the hardest part to calculate. So here it is very true that we just look at it and we can guess. We'll see, we look at slightly more complicated problem, but of course we go to partial differential equation, it just gets completely out of hand. We look at the Laplace equation, and you say you want to find all solutions, very non-trivial. Okay, it's hard to even to know when you have all of them. Okay, not just you and give it to a mathematician, to know when you've gotten all of them is very, very difficult. Alright, so you have to count in some funny ways. Okay, to make sure you've got them all. Right, so even this step is non-trivial. You have to pay attention to it. Otherwise you cannot do the next step, which is to satisfy the boundary condition. Okay, so in this case we get lucky, so one dimension null space, we're thankful, we got it. So now what do we do? Right? How do you do the null space? But once you do the null space, you have to now try to find the right inverse for everyone. So what does the null space have to do with the right inverse? So let's think about it. So I'm trying to solve this equation now. So I'm going to drop the boundary condition. So let's write it over here. So what does the null space have to do with the boundary, with the null space solution? Right? Seems like weird. So let's look at it. So if I look at, I have this fat matrix conceptually in my head, A1 sitting over here. Right? To find the right inverse, I need to find a column that satisfies this property that, so to find the ith column of the right inverse, I put 0, 0, 0 or 1, 0, 0, 0 like that, right? So in the ith position, I put a 1. Okay, I need to solve this equation, ax is equal to 0, 0, 1, 0, right? That's what I want to do. If I can find this, then I can have found one right, for the right inverse, I found the ith column. And I need to do for like the first column, the second, the first column, the second column. I need to find for every column to solve the equation like this. Okay, the trick is this. The trick is to observe that if I look at the top, so ignore the ith equation. Okay, so ignore the ith equation, which has the 1 in it. If I look at all the equations above the ith equation and all the equations below the ith equation, the right hand side is 0. Right? Which is exactly the same as homogeneous solution. Right? If I look at A1 xh is equal to 0, all the right hand side is 0, for which I know all the solutions. So at least for the first few rows, the last few rows, if I know this equation in the middle, I can actually write down solutions beside for the right hand side. Okay, this is the first observation. Okay, so if I know the homogeneous solution, I can write down solutions for this, which stands for the top part and the bottom part. Okay, the next thing is somehow to take this solution and stitch them together in such a way that you can also solve the guy in the middle. Okay, remember, we are going to take arbitrary linear combination of the null space for the top part and the bottom part, and they still give you the zero. Right? So the linear combination is still up to you. For us, we are very lucky linear combination with just one dimension, so we just pick this constant C. Right? So if you can do it in a very clever way, we might be able to finagle a way to satisfy the guy in the middle. Okay, so we're going to have to go through the detail of how this is done. But that is the big picture. The fact that so this is called what we call delta n minus I in this equation. So that's the right hand side. Okay, so how do you do it? So the idea is we reduce one for every position of the one. Okay, this is where the translation symmetry comes in. This is what you get the convolution. You look at this matrix, right? If I put a 1 on the right hand side, so I put a 1 somewhere and a 0. So 1 goes to 0, 0 like that, whatever. Right? Let's say I put it in the 10th row, starting from 0. Then of course the 10th row has this 1 in it. But if I forget to tell you which row I put the 1, you could not guess it either. Right? Because this is the same, every row looks identical. So if I don't tell you where I put the 1, you obviously cannot tell by looking at this equation where I put the 1. Therefore the solution I construct for the 1 in one position must be the same solution for the other ones here. Right? So that's the key thing. You can just translate the solution, you can get those ones to go to everybody else. It's called translation symmetry. And it's much easier to check by writing the equations down. Okay, so what is the equation I solve in this case? Okay, so let's say that I put the 1 for now n equal to 0 for me. Okay, that's the one that's easy to see, it's not so arbitrary. So let's call the solution of H and conformity with lecture engineering. It's called impulse response. They usually call this solution when you put the 1 and the 0 protein as H because this H supposed to remind us household them. It was the first to do it this way. By computing the right inverse. Never called that. I think we're talking about operator inverse, but anyway. So how are we going to solve this? So we write down the equation, you see that this is H of n plus 1 minus lambda of H of n is equal to delta of n. That's how people write it in engineering, right? What this tells us is that if I was saying I wrote down all the equations explicitly rather than matrix notation, the equation looks like this and a little bit more pleasant this way. At time 0, I have H of 1 minus lambda times H of 0 equal to delta of 0, which is the 1. Okay? If I look at time, so this is n equal to 0. If I look at time n equal to minus 1, I have H of 0 minus lambda of H of minus 1 is equal to delta of minus 1, which is 0. Right? So, and so on. And if you look at n equal to 1, we have H of 2 minus lambda of H of 1 is equal to delta of 1, which is 0. Right? So remember, this is the oddball equation. The right hand side is not 0, but everybody else it is 0. Okay, now you notice, so now is the first time we actually exploit the fact that the number of non-zeros in each row is only 2. There will be 2 non-zeros in each row. So if I look at the diagram now, this is my n-axis. Right, this is n equal to 0, 1, 2, like that, minus 1, minus 2, and some. Right, I'm trying to find the sticks that correspond to h of n, like that. This is h of 0, this is h of 1, h of 2, h of 3, h of minus 1. I'm trying to find these numbers, so I should stick in such that I can satisfy the equation, right? So that will correspond to the one column of the right inverse of h. But it will be the column in the zeroth location. Because I put the 1 this time in the zeroth location. Right? So this is the right inverse I'm trying to construct. Right. So now if you look at the equations, you notice that if I look at the equation for n equal to 1, it only involves these two numbers, h1 and h2. Right? If I look at the equation for n equal to 2, it will only involve the next two numbers. Right? So these and so on. Right? So from n equal to 1 onwards, the only numbers I see in the equation are from this side. From n equal to 1 to 5. Right? And furthermore, always the number on the right hand side is a 0. 0, 0, 0. It's the same as homogeneous equation for which I know all the solutions for this form. Right? So I know that if I look to the right hand side, this homogeneous solution must be some constant, which is typically called C plus times lambda part of that. Right? The only choice you have is in that constant. Every solution must look like that because it is part of the homogeneous solution. Alright. Now what about if I look at these equations, n equal to minus 1, n equal to minus 2, and so on. So let's write it down. Minus 2 will be minus 2 plus 1. Delta of minus 2 equal to 0 and so on, right? So you can see if you look at the equation at n equal to minus 1, it involves h0 and h of minus 1. Look at the next one, h of minus 1 and h of minus 2, like that. Right? So if you look at above, from n equal to minus 1 all the way to the back, all of these guys lie on a separate homogeneous solution. They must have some homogeneous equation too, and we know all the solutions of that. It has to look like this, there's no choice. Therefore, we know that all of these numbers must be picked again from the same space. Right? But you can pick a different constant now, right? Because these numbers have nothing to do with those numbers. They satisfy two separate sets of equations. So you're free to pick these two numbers, C plus and C minus, any which way you feel like. You're guaranteed that infinite number of equations will be satisfied except this one. Right? Okay, so we've stitched together the Green's function from pieces of the homogeneous solution. Okay, and that's why the homogeneous solution, we see them from places they go. So we're looking at a solution for the inverse, one column at a time. Most of the time, right hand side is 0. We're going to exploit that symmetry to assemble the numbers that you need to stitch together this column of inverse. All right? So now we're almost done. Why? Because we have two constants in H, and we need one equation to solve. So I should be able to find plenty of solutions. And that's good news, right? Because we know for a fact maybe the right inverse is not unique. There's be plenty of solutions. Hopefully this guy will find them all actually. And actually you can prove it will find them all, but you don't know that's all, okay? So now we're done. So we know, so let's write it down. So h of n, our guess right now is two parts. So it's going to be c plus lambda power of n, and n is greater than 0. In this case, greater than 0. Be careful about that, huh? It's from h1 onwards. And it is c minus lambda power of n if n is less than or equal to 0. Right? And that's because this line will shift slightly depending on how you write down the delta function. For me, the delta function I solved was like this one. Notice that for most electrical engineers, this would be considered to be not in canonical forms of that. Right? Some communities will write this as h of n minus lambda h of n minus 1 is equal to delta function. You write a line. This is much more conventional. Right? If I do that, then this line will shift over by 1 like that. We'll say c plus from here and c minus from there. But of course, this is just linear algebra. Numbers are numbers. It doesn't matter how you want to do it. But once you pick this equation, then you must argue all your way through. Okay? If you pick this and you pick that solution, you'll be wrong. Okay, so be careful. Okay, so don't do it mechanically. Make sure that you think it through rather than just memorizing. Okay. So now we're good. So the only equation we have to satisfy is n equal to 0. So n equal to 0, the equation is h of 1 minus lambda of h of 0 is equal to 1, right? So now we plug it in. So h of 1, n equal to 1 has to come from this branch, so it is c plus lambda power 1. And h of 0 has to come from this branch, right? That's cast in stone. It is c minus lambda power 0 is 1. Right? And we get c plus lambda minus c minus equal to 1, and this is called the jump condition. Right, so I think it's called jump condition because they think of this the right hand side of the input signal, so it's initially 0 and it jumps to 1 goes back to 0. And the impulse response is following the 0 input response, and the 1 comes with the jump and go on to different. That's called the jump condition. It uses the impulse response system to jump when it sees the input. It makes the output jump when the input jumps. Yeah, so it's called the jump conditions. Right, and this is the 1. So from this you can see that there's one free variable. So if you say for example, you want what's called a causal solution. Okay, so in this case we're saying if I want a causal solution, then we're saying that we want h of n, so let's write it out. 0, h of minus 1. Right, so for electrical engineer, this is time, all products of time. There's no input until time n equal to 0, and then there's an input. So we don't want the output to come alive until this. So then if all of these numbers 0 is called a causal impulse response. So you get a causal impulse response we pick C minus to be 0, and we pick C minus to be 0, then we have to pick C plus to be 1 over. That's the causal impulse response. It corresponds in the right inverse to picking a lower triangular right inverse. Right? Why? So let's just think about it. So now that I know H, how do I assemble the right inverse? Right? So assemble the right inverse, and I do it like this. Right? I take my 0th column to be a little bit bigger, H0, H of minus 1, minus 2. So the impulse response that I just computed, because this is the column, the 0th column, the right inverse. Right? To find the next column, if I want to find the next column, I have to solve the equation Wn plus 1 minus lambda W of n is equal to delta of n minus 1. I need to push the 1 to the 1 and 1 rather than times 0. I need to push this 1 down over here. That's called delta n minus 1. But it's easy to see that the solution of this is just to move the old solution down by 1. Right? So you just move, take your old numbers and just like, because the 1 split down, just move all the h down by 1. Right? Because these rows are exactly the same. So the right hand side slides down by 1, just move all these numbers by 1, you satisfy the same equation, but you can't have a difference. Right? So this is called cancellation invariance. Right? So therefore we know that the next column must be this column split down by 1. You can pick other columns too, but that's here 1. Minus 1, minus 2 like that. And if you want at time putting minus 1 is sliding up by 1 instead, so you get h0, h of minus 1, 2. You see that this matrix is also a Toeplitz matrix. It's constant along the diagonals. Okay, so once you know the impulse response, so one column, the right inverse is called the impulse response, because this is called an impulse, and this is called the output is called response. Right? What is the gain function? Once you know it, once you place the delta function at one point, you can find the rest by just moving things around. It will not happen always. Huh? Sometimes if you move the delta function, you get a different equation, completely different equation, you solve it all over again. Okay. But if it's constant coefficient, as they say, then you should have this translation invariant, and you can get the rest of it just by moving it around. So you don't need to solve an infinite number of equations, you just need to solve one guy by this zero input response technique. So you just move them around to get a right inverse. Okay, so you're guaranteed now that if you take A1 and multiply by this right inverse, or A1 right inverse, you're going to get a bunch of delta functions. 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, which is exactly what we want. Right? Computer right inverse. Notice there are many possible right inverses. Why? Because I can take any solution of this equation and add the homogeneous solution to it. Right? If I find that impulse response, I can add to that any other constant times lambda power and I get another solution. So the right inverse is far from unique. And you can even change the impulse, the zero input from column to column to column. You have a right input that is not at all focused. You have to be careful about that. There are infinitely many right inputs. Okay, we pick this one because of this nice structure in it. It's easy to pick. Right. So we have the right inverse. Right? Okay, so we almost get done now. Okay, with this we are done. But let's just go back and take one last look at it. So if I pick, remember there are two constants I can pick. I can pick this one. If I pick this one, then h of n is usually written as like that, lambda power of n times 1 over lambda for n less than or equal to 0. Sorry. So this is the right one impulse response. It will be C plus, so it will be lambda power n minus 1 for n greater than 0, and it will be 0 for n less than or equal to 0 like that. So right drawing response, that's one choice of these ones. You got to make a choice. You can't leave variables inside this matrix. Okay, so write a right inverse. You must put honest to God numbers inside. So you must make a choice. Even there are many of them, you must make a choice. So this is a very popular one. You want to pick a left going impulse response, so picking C plus to be 0, and picking out what C minus is. That's possible. Sometimes electrical engineer will pick two-sided impulse responses because they don't want the impulse response to blow up, they want it to be summable. They make two-sided. So again, coming back over here, when you pick that part to be 0, if you pick that part to be 0, then it becomes lower triangle. So if I pick a right going impulse response, I'm saying I'm going to pick a lower triangular right inverse. Conceptually, you could have done that in one shot by saying, pretend that the main diagonal is on the top, is a lower triangle matrix, write down as inverse. You should go back and check that that is an inverse for this matrix. Okay, so infinite dimensional matrices do not behave like finite dimensional matrices. Okay, you can be non-unique and have inverses. Very good. Okay, so you just pretend this is square. You complete the inverse, you will get that one. You will done it by a shortcut trick. Okay, so in most graduate systems, they just say the inverse of this is a lower triangle matrix. It's exactly this matrix with the numbers filled out with these numbers. Okay, 1, lambda squared, lambda cubed, like that. Okay, let's say it's 2 by the geometric sum here. Okay. Similarly, I could have also picked H being anti-causal, in which case H is completely upper triangle matrix. It will be non-zero on the top, everything below will be 0. That is the same as saying that I'm going to view this matrix as upper triangle matrix and take its upper triangle matrix. Okay, so you know that. That's another way to think about it. There's another way based on complex analysis too. Okay, but you have to be careful that these infinite dimensional matrices do not behave the way you think finite dimensional matrices behave. Okay? That gives you some ideas to look at it. You must verify everything by computation. There's no grain table theory that tells you what it is. So be very careful about it. I've seen many people make mistakes about it. Alright. Now we have the right inverse, we're almost done. We can go back to our grand scheme of things now. So we have the right inverse, so we go back to that system. So let's put it all back up the right way. So here's the right hand side of my equation, which are known to me. Right? This is the unknowns, u, u0, u1, u of minus 1, like that. And then I have this last row that I did, right? That's the back end. 0, 1, 2, 3, whatever, like that. And this side is bounded in between. Right, so I still have one more equation to solve in this case, but that's now easy to do. I just first find a particular solution. Okay, so to find a particular solution, so remember I took the matrix A, I split it into A1, A2, U is equal to B1, B2. Right? We solve the first part, A1, U is equal to B1, by saying U must be a particular solution plus the homogeneous solution. To get a particular solution, we know A1 is the right inverse, so we can just take it to be this one. Right, so that's easy to do now. You just fill in these numbers from the H's appropriately and multiply by V1. Okay. So here you'll be careful now. Until now, we completely avoided infinite sums. Notice I never wrote an infinite sum so far. So very cavalier about what I did. But now when I multiply by the right inverse, you do have a proper infinite matrix like that. Okay, so it could very well be that you try to do the multiplication, nothing wants to work. Okay, so what you do is, okay, let's look at one multiply, right? Let's say that I have these x's over here, so x0, x1, minus 1 like that, right? Let's say I want to multiply by this row. So this h0 will multiply the x0, the h of minus 1 will multiply the x of 1, h of minus 2 will multiply x of 2, that, and then h of 1 is sitting over here. Multiply x of minus 1, like that, right? We do one row times one column to get this number, the zeroth position over here. This is sum I have to do. This is an infinite sum in general. Alright. Alright. So the question is, does the sum converge or not? Notice that this is also for electrical. Notice that if you look at the sum of these guys, it's all adding up to 0. So of course, this is just a convolution of h with x. Period time and equal to 0. So that's the number we got that. So the convolution formula is just multiplication by a Toeplitz matrix. That's what we call convolution. For the rest of the world, don't worry about it. We just multiply this Toeplitz matrix to the right hand side. The question is, when I multiply, what happens, right? If this infinite sum converges, well, great, right? If it converges for one, you can prove it's going to converge for everybody else. Okay, the theorem easy check. What's going to happen? So, what happens if it doesn't want to converge? Right? If the sum doesn't want to converge, what are you going to do? Well, you have to go back. Remember, we had degrees of freedom over here. Right? We made an arbitrary choice of C plus and C minus. You have to go back all the way now to this part, change C plus and C minus to something else, and then come back and try again. Of course, it's an extremely tedious process, so you would like to know is there one short way of doing it. Right? And there are, so usually electricians will pick C plus and C minus. Such that this impulse response, so for one-dimensional system there's not much to do, so we can prove that either it wants to do this or it wants to do this. Okay, so this is the only two choices for this particular computation. Either blow up to the right or it will blow up to the left. Okay, so I'm pretending that in this case blowing up to the right. So you usually try to pick the one that's not blowing up. In this case, it will be a left drawing solution, and you hope and pray it works out there. If it still blows up, why? Because x might be blowing up to the left. Then you have to switch and try the other side. Okay? If both blow up, what do you do? Well, if both blow up doesn't mean there's no solution, it just means that this attempt failed. Okay, so like I said, this is all big. We're not deriving the solution, even if it feels like that, we are not deriving the solution. Okay, if both blow up, then basically you're in trouble. Okay, very well could be that there is no solution, but it will require other efforts to show there is indeed no solution. Okay, but usually in class, in undergraduate class, we always pick it such that if you make one of these two choices, it will actually work. Okay, the most trouble we do is to force them to pick the right one. This particular one is very fond of, and I think it's called a stable solution, and so because it's unstable. Okay, so you instantly pick that one, but it's not guaranteed. Alright, so anyway, so when you do this multiply, you're trying to be careful. Check the sum is absolutely summable. Okay, so make sure that this sum, for this sum to make sense, you must make sure that this sum, you multiply every entry in x of minus and add it up, is less than infinity. The sum must be absolutely summable. Conditional convergence is not something that an engineer will tolerate. Okay, that's no meaning in real life. Something is conditionally convergent. Remember this sum that I gave before: 1 minus half plus 1/3 minus 1/4 plus 1/5 minus 1/6. The sum, the alternating harmonic sum. So this is the alternating sum. The numbers in the sum are going to 0. So it's very trivial, right? You can easily go through. I start from 0. I add a 1. And I add a half. Subtract a half, and add a 1/3, and I subtract 1/4. You can see from this that it's obviously convergent, right? That's the alternating convergence theorem. Right? This sum obviously converges. It actually converges to log 2, I think, or something like this. However, that is a meaningless number. Why? Because if I put everything plus, sum is actually infinity. It's not some nice number. Okay? It's an infinite string. You're folding it up. You can make it converge to whatever you feel like. Okay, so from a mathematical point of view, the sum, the alternating harmonic sum has no meaning. Of course, it rises in Fourier series all the time, and then you try to finagle it so that some other thing will work out correctly. But this is the final answer, it has no meaning. Okay, so you should not allow it. Okay, what to be clear. If it's absolutely converging, it has meaning, we add it up and go. If it's not absolutely converging, then something else has gone wrong somewhere else. You've got to walk your way back all the way to what you're trying to do and figure out what to do with that sum. Okay, there's no such thing as a right way to sum up this. You can't say left to right summation is always right. You must pick some other ordering depending on what you're trying to do. Maybe no good ordering. Alright? So anyway, you check the sum. If you can do that, then you have, if the sum is converging properly, perfect, and you have a particular solution. Right? So now we can say, well, I'm going to take my particular solution to be A1 right inverse of x. Right? And it's absolutely converging. Not absolutely converging, try some other 8. If you cannot find one, then this method has failed. Now that there is no solution. Yes, we can say that it fails to find a solution. Okay, so now here we know that the general solution will be UP plus C times lambda power of x. So a better way. So U must be this solution, x plus C times this power. 1 lambda squared. So that's the solution. Particular solution plus the marginal solution. So now we're almost done, right? We only have one more equation to satisfy. So we plug it in over there, and we're done. Okay, so we have this sum to satisfy n times u of n must be equal to 1. Right? So only one equation left, and we have only one unknown to fix. We plug everything in, n times dt of n plus n times lambda power of n times constant equal to 1. Okay, again, before you open the sum or do anything, you must make sure that it's absolutely convergent. If it's not absolutely convergent, you're in trouble already. Okay, there's no way out unless you have some other way. You walk all the way back and look for some other way to do it. Okay, so if this sum is converging, remember this is already computed number. If this is converging, you can split it out. Right, and then like a summation n times lambda power of n is equal to 1. This has to be converging too. So all the numbers inside are converging, you get c to 1 minus and that is the last constant that you need. plug it back in over there, you actually have found a solution. It's a unique solution. Okay, that's the process. Alright, so try to do this process yourself. You don't need to go over what I did, you just have to go back, throw everything away, sit in a quiet room, and then do the whole thing yourself one time. Okay, it's important that this is the simplest system of infinite equations you can think about. If you cannot do this in a dark room with no books, no internet by yourself, there's no hope of doing something else. Okay, this is the absolute simplest equation I can think of. Okay, so you first go back and you do this one by yourself. Okay, make sure you understand it completely. Alright, we good? Okay, so do that one, make sure you understand it, and the same technique will apply to differential equations too. Okay, so then, once you understand this thoroughly, you should be able to go back and see this equation also as this special case of this, or a slight technique what I would call it, of the differential equation case. Okay, so you're going to go back and do this one too. du by dt minus infinity. We should go to do this one and say, let's say the boundary condition in this case is this one. It's integral from minus plus infinity t times u of t into we're going to do this. Make sure that you be methodical about it. Please understand why you're going to do this, understand where you're guessing, how you're guessing, what can go wrong, how make sure when you're picking the three variables when you're not. Okay, make sure you try to relate this to the finite dimensional linear algorithm you're running. You're trying to understand how to deal with the large system of equations. Okay, and the theory is hopefully helping you guess, check, keep going, making stuff. Okay, do this. So once you do this, then the next one we're going to talk about is that you can actually compute a factorization of this matrix. The matrix can actually be factorized also. It's very surprising that you can actually factorize this matrix. You can factorize this matrix using the Fourier transform. Okay, so I'll say just a few words about that in the next class. So there's actually a way to write this matrix and here as call this A1, correct A1 as F, and you can actually factorize it, and this factorization is usually thought electroneous in the guise of Fourier transforms of a block. And that's why transforms is also a technique to solve this equation, because you can actually diagonalize this matrix by this Fourier matrix. Alright, so we'll get around to it, but please go through the different system of equations, and then next up we'll start with eigenvalues now.